What was it? So first of all, what's a sequence? A sequence is a list, right? A sequence is a list. The series is when you add up all the elements in that list. Okay, that's our baseline knowledge. Everything goes from there. All right, so then we had a geometric series. What was a geometric series? Who can remember that? Yes, sir.
The sum of a geometric sequence.
Okay, good. The sum of a geometric sequence. And we had a kind of a varied form of that, right? When we talked about a series, we wanted to get the ends just right, and we allowed for a coefficient. So we said this, right? So we want the first exponent to be 0. But we want n to start at 1, so that still means the first term, right? N equals 1 means the first term, but we want this exponent to be 0 in that first term. So we do r to the n minus 1. And then we have this coefficient a, right? We have this coefficient a. And so really, what is a geometric series about? Each term that you have, how does it compare to the last term? So that's really what a geometric series is about. Any given term, what's the next one you're going to add to the list compared to the last one? What does that tell us about that? What's the next one like compared to the last one? What's that? Someone said it. Griffin? R times the one you had before. Is that right? Yeah, because so really, n is telling us how many times we're going to multiply by r. So when you go on to the next one, you multiply by one more r, right? So it looks like this. You keep, to get the next term in the sum, you're going to multiply the last one by r. That's exactly what a r to the n minus 1 means. And that's our geometric sequence, right? You keep multiplying by one more r each time. Okay, so I think we did the easy example of the, and remember, for what values of r does the geometric series converge? What do we say? Between -1 and 1, the same as the sequence, but then also the sequence converges to 1 when r equals 1, but what about the series when r equals 1? Infinity, right? Because you're going to keep adding a over and over again. That will get big, okay? So the series will converge only when r is between -1, and what does it converge to in that case? No, the series. The series. Yeah, the sequence will go to 0, which we need in order for that sum to sum up to something. What does it sum up to, remember? We did the derivation last time. It sums up to a over 1 minus r. We talked about the turtle, right? The value of r for the turtle crossing your hallway in your dorm or your apartment building was r was 1/2. You always add on half the distance it went before. So it's always going half as far to the wall as it did before. And as long as you could add up all infinitely many of those days of progress, the turtle would make it. It would make it to the other side. And so that whole thing equaled 1, right? So that thing equaled 1. And we did 1/2 over 1 minus 1/2. And we saw that that the sum of all those when r was 1/2 and a was 1/2 equal to 1. All right, so let's try a harder one. Another example. Make that a little bigger. All right, so first of all, does it qualify for a geometric series, or can we make it a geometric series? And the answer is yes, because our n is in the exponent. That's what a geometric series is. Multiplying by one more r each time means r to the n. And so if you have your n's are in the exponent, then this is geometric series. But we just have to have a work to do to make it look like that. So we need to make it look like, in the end, we need to make it look like something times something to the n minus 1. So we really have to know what our exponents mean. So that was one of the things on your quiz. What does -3 to the n plus 2 mean? What does -3 to the n plus 2 mean? Right here in the gray and blue shirt. Yeah. Right, okay. So, but we need n minus 1. We need to show n minus 1. So how are those different? How is negative 3 multiplied together n plus 2 times different than negative 3 multiplied n minus 1 times? You got to think about that. How many more? So see, this has how many more negative 3's than this? 3 more, right? So to keep it n plus 2 negative 3's, what am I going to do? I'm going to multiply by 3 more negative 3's. Did you see that? Now I have n plus 2 negative 3's multiplied together. Because I have n minus 1 of them and then 3 more. And that makes n plus 2 total negative 3's strained together, multiplied together. Okay, what about... So actually, I wanted to do that over here. So I got negative 3 cubed times negative 3 to the n minus 1, first of all. What about this 4? We need that 4 to be to the n minus 1. So how are those different? I need one more 4. One more 4 here. I need one less 4 now, right? You see? Here I've got n minus 2 4's. This is one more 4, n minus 1 4's. So what can I do to undo multiplication one time? Divide by 4, right? Or times 4 to the negative 1, right? So I can do 1/4. Yeah, let's just do 1/4. So do you catch it? This is one more 4 than this many 4's. So if I divide by 4, now I've got the n minus 2 4's that I need multiplied together. And I also have the 5. All right, so back to this now. So what's my r value here? What is to the n minus 1? Negative 3/4 to the n minus 1. And then what's everything else that's going to go out in front of that? All this stuff, right? So it's going to be negative 3 cubed, which is negative 27. And then dividing by 1/4 is the same as multiplying by 4. Would you buy that? And then over 5. So that all becomes my a value. I had to factor out 3 negative 3's, and I had to get rid of one. I had to have one less 4 taken out. Okay, so now it fits the form of our geometric series. What is the value of a and what is the value of r? A equals, well, whatever that is. Just leave it that way. And what's the value of r? You're all thinking negative 3/4, and then we say, is this a convergent or divergent geometric series? Convergent or divergent? How is each term, so just what is each term compared to the last term in this sum? To get the next term, you do what? Multiply by negative 3/4. So basically you just keep multiplying by negative 3/4 to get the next term. So what's going to happen to those terms? You're going to keep it smaller, right? You're going to keep taking negative 3/4 of those. And so our sequence will eventually get to 0. And whenever the geometric series has an r between negative 1 and 1, it converges. Okay? So it converges to some ugly number. 27 times 4 over 5, all over 1 minus negative 3/4. whatever that turns out to be. But if you were able to add up all infinitely many terms of this series, you'd get this value. If you add up a partial sum of them, you'd have some approximation to this. And the longer your partial sum, the better approximation it would be to this, right? With every term that we add, we get closer and closer to this sum. Right? So any partial sum, say take n equals 1 to 100, the first 100 terms, would be a pretty good approximation to this. But it wouldn't quite be right. You'd be off by what? The sum of all the rest of the terms. Okay? So any partial sum would be a good approximation. If you're able to add them all up, then you would get exactly that. Okay. Any questions? Anyone having to put that in your calculator? Negative what? Over 35. So what is that? That's about 13, negative 13, something like that? Yeah, negative 12, negative 13, something like that. So the more terms you add, the closer and closer you're going to hone in on this sum of negative 12.3 or whatever. Okay, questions on that example? Okay. So let's talk about a series called the Harmonic Series. So we're going to do some, this is not a geometric series. The Harmonic Series is a really fundamental series here, and it's simply 1 over n. Okay, so what about the sequence, 1 over n? What can you conclude? 1 over n. Is that convergent or divergent? The sequence, 1 over n. Can you write it out? So, see that, think what? See that, think what? Go. See that, think what? Tell me. Did you get it? No, but what does this mean when you see that? Uh-huh. Right, and you said it converges to 0. Why? Okay. Yeah, right. So you're just getting a smaller and smaller fraction. Okay. Is this anything we've seen before? What is this? This is a p-series with p equal to? P equal to 1. And for what values of p did a p-series converge to 0? As long as p was greater than 0, right? So 1 over n to the 0.02. That converges to 0, just a whole lot slower. It'll get there a whole lot slower than this one does. But it'll eventually get really small, okay? 1 over n to the 0.2. So that's a p-series with p equals 1. So the harmonic series is a special, sequence. We were talking about sequence there, sorry. So the piece, so now we're going to talk about p-series, okay? P-series is when you're adding up the terms of a p-sequence. The harmonic series is one particular p-series when p equals 1, right? So or the p-series when p equals 1. Okay? See this right here, think what? See this, think what? So can you tell me right here? Right. It's just going to be the sum of those things we had in the sequence. So what did we say? With the divergence test, we said if that sequence goes to a non-zero number, or it diverges, what do we say about the series? So if the sequence approaches something like 1/3 in your quiz, those numbers get closer and closer to 1/3, then what about the series? Divergent. You end up summing the same number together over and over forever. Okay? What about this? What about this sequence? The sequence goes to 0. So we're adding a smaller and smaller value. We're adding a smaller and smaller value. So what about this series? Convergent or divergent? Okay, well, let's take a look. How can we find out? So the sequence is going to 0. So eventually we're going to keep adding very, very small values. Okay? And so it's kind of like the series has a chance, right? The series has a chance, but is it guaranteed? Is it guaranteed that that will sum up to something? So let's do something here. Let's look at this comparative sum. So what did I do here? So these are the same. Okay, now I want to group these three together right here. These three together equal what? Those equal 1. Is this sum greater or less than those added together? So I got 1/2 plus 1/3 plus 1/4 versus 1/2 plus 1/4 plus 1/4. This greater or less than 1? Greater. This is greater than 1. Okay? Now I'm going to take these 4. What do these 4 add up to? So 4 1/8. Actually, let me start over. I want to do 1/2 at a time here. Okay, so these are the same. Sorry. These are the same. These are the same. I want to add up just these 2 compared to those 2. All right, so 1/4 plus 1/4 equals? Equals. That's 1/2, right? And this is greater than or less than 1/2? Greater than 1/2. All right, now I'm going to take I'm going to gather together the next 4 terms in our harmonic series and compare it to 4 1/8 added together. What about 4 1/8 added together? That equals 1/2. And how does this compare to 1/2? Greater. Now I want to take the next 8 terms and gather those together. Okay? From 1/9 to 1/16 and compare that to 8 1/16. What is 8 1/16 added together? 1/2. And how about the actual series adding 1/9 up through 1/16? Greater than 1/2. Okay? I can always take, so now the next time I'm going to take, let's see, this is 8. Now I'm going to take what? I'm going to take the next 16 terms and compare it to 16 1/32 added together. And those will be 1/2. And what about those 16 terms? Greater than 1/2. What about this series down here? Convergent or divergent? Well, can I ever run out of enough terms to double and take the next double amount? I'll never run out. And so I can always take twice as many as I had before. So 16 1/32. Then what? 32 1/64. Then 64 1/28. I can always get twice as many terms as before and have those equal 1/2. So what about this one down here? Convergent or divergent? Divergent. I can make it, I can arrange things so that I'm always adding 1/2 over and over again, just by taking twice as many terms as I had before, and I'll never run out, because n goes to infinity. All right? How does this sum compare to this sum? It's bigger, because so all those groupings, I always have to make bigger than 1/2 each time. So I've got a divergent series, because I end up just adding 1/2 over and over again, and then our harmonic series is bigger than that. So what about the harmonic series? Divergent. Divergent. So what's going on? I thought that if the sequence went to 0, the series would add up to a finite number? Okay, so what we're seeing is that it's necessary for the sequence to go to 0 in order for all those terms to add up to something finite. But that's not enough. That's not enough because I've got this example of that where all the terms are getting smaller and smaller to 0, but I sum them up, I still get something too big. It's just going to keep getting bigger and bigger. Okay, so he was onto it. What do we need? In addition to the sequence going to 0, I also need what about the sequence? It needs to get to 0 fast enough, right? Those values need to get small, close to 0, at a fast enough rate so that this doesn't happen. Okay, so we've seen that principle before, right? With the improper integrals, right? Improper integrals. We saw that some rate functions, they went to 0, but then the accumulation still got infinitely big. But then if the rate function got to 0 fast enough, then that accumulation function would level off. We talked about that, right? It's the same principle here. So you can kind of think about the sequence is like the rate function, right? And then the accumulation is like adding up those terms. Okay? So we know that 1 over n is divergence. Okay, so then what about 1 over the square root of n? Let's start with this. Does that sequence go to 0? If the sequence doesn't go to 0, game over, right? If the sequence doesn't approach 0 in the end, we can just stop the conversation. Why? By the divergence theorem, it's divergent. The only series worth talking about are the ones whose sequences go to 0. Otherwise, it's over. It's just over. You're gonna try to add those up, and it's never gonna add up to anything. Never converge on a particular sum. Okay, so what about this? 1 over square root n. So see that, think what? Go. See that, think what? Write it out. Oh, in the green shirt back there, tell me. When you see this, what do you think? What is that? Okay, good. You said 1 over 2, that's good, square root of 4. All right, so does that sequence, 1 over square root of n, go to 0, converge to 0? It's a p sequence with p greater than 0, right? P equal to 1/2. What about the series? Convergent or divergent? Some people are saying divergent. Why? How do you know that? Okay. Therefore, good. Good. So square root of n, those are smaller numbers than our denominators up there. So what about these fractions compared to the harmonic series? They're larger. Every one of those fractions, except for the first one, all those fractions are bigger numbers than the harmonic series. And we know the harmonic series diverges, therefore, you've got everything, you've got a bigger sum than that. Okay, so this is the principle of the comparison. You've got one that you know diverges. You can come along and say, oh, here's another one, and I can show that every one of those terms, or at least starting at the second term, all those terms are greater than the terms of one that I know diverges, so that's got to diverge too. So let me show you that visually. So here is looking at the harmonic series as, there's the harmonic series. as a sequence. So what does the series mean? The series means add up the y values of those points, right? So 1 over 1 is 1. So the y values of these, right? The y values. 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. All right, so the harmonic series would be to add up all the y values of these points. And what will happen if we add those up? Converge or get big? It's the harmonic series. The y values of these points are the harmonic series. Add those up. Blows up. Divergent. Okay, so what about 1 over the square root of n? So where will those points be? So the red is the harmonic. The y values of the red points is the harmonic sequence. The y values of the blue, the y values are what? And that's actually another what? P, that's a P sequence with P equal to what? 1/2. Does the sequence go to 0? P sequence. P is greater than 0. So the sequence goes to 0. But what? Add all those up. Clearly, those are going to diverge. Why? Because they're all greater than one we know already diverges, right? All those particular values are greater than the values of the harmonic, which we know you add them up and it diverges, so that will certainly diverge. Okay, now I'm going to leave square root up there. I'm going to show you another one. How about purple? So what do we know about 1 over the series 1 over square root of n? We know that it converges or diverges? Diverges. The sum of the y values of this sequence, 1 over square root of n, sum those up, that diverges. What about this? So now I'm showing you a new one here. Convergent or divergent? So I know the y values of the blue one, the blue points, those sum up to infinity. What about the y values of the pink points? It should make sense. You can't tell. You don't know, right? So you could have a series whose terms are all lower than 1 that could be either divergent or convergent, right? So the comparison test, if you're comparing to get divergent, you have to have a divergent series, and then the one you're looking at has to have terms that are all greater, and then that would diverge. But if you have a divergent series, and you have all terms that are lower, jury is out, right? Who knows? It could be convergent, could be divergent. Okay, what is it? So it ends up being, this is 1 over n to the 0.9. So the pink one there is 1 over n to the 0.9. So now you can know. Divergent or convergent? Divergent, because those are greater than 1 over n. Okay, one more thing. Hold on. Shoot. Okay. So the comparison test, that's what we said. So if you have two series with all positive terms, you know this one Bn is a divergent series. And the one you're analyzing, An, you know all of its terms are greater than or equal to all the terms of this known series, then the one you're analyzing is divergent. Okay? So what I was going to have you do, but we're out of time, is write the convergent version of this. What's the convergent version of the comparison test? Okay, so the one you're analyzing AN, you have this other one BN that's convergent, and AN, all the terms are less than or equal to the terms of BN. That would be the convergent version. Okay. Look, I'm going to update Blackboard and it'll show you everything you need for Wednesday. There may be written, maybe more than one web work. See you then.